Okay, so I'm aware that you couldn't really have done this before lecture today, so I can give you guys time to work on this if you want, or I can just go over it. I'll have no idea how to tell when you guys are done, so yeah, that's probably a better idea. If I'm ever going too fast, just tell me to slow down so you can keep up, but yeah, I'll go over this, assuming you've at least looked at it since you did lecture this morning. So number one is just asking to determine if these molecules are dienes or if they're conjugated or not. Can anybody describe what it means to be conjugated? Oh, okay. Alternating single and double bonds. Yeah, that's a good description. So basically just there's only one single bond in between two double bonds. There's not multiple single bonds in between them. So this first one, is this a conjugated system? Yes, it is. I'm just going to circle the ones that are conjugated, and it's conjugated because there's alternating single and double bonds. There's only one single bond here between the two double bonds. What about this one, bottom left? This guy is what I'm referring to. Is that conjugated? So remember, we have to have alternating single and double bonds. So yeah, I'm looking at bottom left. Yeah, okay. So this is no. I guess we'll just put an X because there's two single bonds in between the, thank you for letting me know you're here. There's two single bonds in between the two double bonds, so they're not alternating. That's not conjugated. They have to be right next to each other. What about this one, top right? Is that conjugated? Yes, it is. Because there's only one single bond, and there's only one single bond, this one, in between the two double bonds, so it is conjugated. And this last one in the bottom right, is that conjugated or not? No, it's not, because there's, again, two single bonds in between the double bonds. So I don't know if you'd ask a question like this, but it's good to be able to identify when something's conjugated or not, just so you know when you can worry about all these new things you learned today. Okay, so this question is just asking to give the 1,2 and the 1,4 addition products from the following reactions. And we're using one equivalent of things we've used to react with alkenes in the past. So I guess I'll go over the 1,2 first, and I'll just show the mechanism for the first one to jog your memory. So like say we're reacting with the alkene, but I mean a double bond on the left. The first step would be the alkene takes the hydrogen, and then the electrons from the bond go to the chlorine. So we get a hydrogen added here, and then a cation that forms here. And this is the cation it forms because that's secondary, so that's more stable. And it's also allylic, now that it's right next to a double bond, so that makes it even more stable. And then the chlorine will come and attack that. So this is the 1,2 addition product, and it's what you guys are used to seeing. And it's called 1,2 because if we start numbering the molecule from where the double bond is, it would be like this. That's also how you would number it correctly, but that might not always be the case. But we added the hydrogen to carbon 1 and then the chlorine to carbon 2, so this is 1,2. If we do a resonance form, I wouldn't recommend drawing arrows like this, like 2 arrows for 2 separate things, but I'm just trying to save a bit of space. So now we have a double bond here, and the cation there. The hydrogen was still added way over here. And now the chlorine would attack that and lead it to this. So the hydrogen was attached to carbon number 1, and then the chlorine was attached to carbon number 4, so that's the 1,4 product. So hopefully you guys remember that from earlier. I'm not going to go over the mechanism for the rest of them because it takes up a lot of space, but it's the same every time. And you're mainly going to see like this kind of thing with hydrochloric acid, but I brought up Cl2 just because he might ask. You don't really have to worry about the mechanism for that either. It's the same general idea, I'd say. So these were the products from adding to the double bond on the left, but we can also look at the double bond on the right. And this is gonna start getting messy, but I guess we'll just, oh, shoot. I guess I'll just draw them. So we have, that's kind of hard to see, but that's the chlorine attached here, actually. Did I not? 1, 2, 5. Okay, sorry, I was confused by something, but this, yeah, this is okay. So this is the 1,2 product, because this is where the double bonds, wait. No, I'm getting confused. Okay, I drew my products wrong. Sorry, I have an answer key I was trying to follow, but I'm just gonna redraw that. I don't remember, I don't know if that was correct, but I'll just do it from scratch. This is where the chlorine should have been. Okay, so yeah, this is the 1,2 product. It looks like I'm doing something wrong. You can ask or like maybe point it out. Like, I'm not always correct. What was wrong with the other one? I'm honestly not sure. It just didn't look right. I think I didn't have enough carbons or something. But I mean, I know this is right for sure. I think I was just a little lost. Well, that's not even correct. Okay, so the double bond was over here to begin with. So we added the hydrogen, the carbon 1, and then the chlorine to carbon 4, and a resonance form occurred, so the double bond moved to carbons 2 and 3. So this is really, really jumbled, but I'm gonna circle the products. try to highlight them. Yeah, I honestly don't know what was wrong before, but it just didn't look right to me, so I did it from scratch. So sorry for confusing you and taking a while with that. When you react Cl2 or Br2 with a double bond, that's just adding 2 chlorines to it. And I guess I'll go over the mechanism briefly with this one. Now it's going to get crowded again. So I don't really have enough space to show the first step, but it's very similar to the attacking of the hydrogen. It just, the double bond attacks the chlorine, and then the chlorine also kind of attacks the carbons, and it forms a cyclic intermediate that you should remember, because you do have to know this mechanism. And then there's like a positive charge here that's kind of shared between everything. And you can basically think of the resonance form doing something like this, kind of. I mean, like, you don't have to worry about showing a mechanism, but I'm just trying to show you how you can think of it happening with the resonance form. So then I would draw this as a squiggly line. There's a positive charge here, and then the other chlorine would come and attack that. I'm gonna erase that to save some space, but that would be the mechanism happening. So this is the 1,4 product and how it would form. We added a chlorine to carbon 1 and carbon 4. It's basically the same as the 1,4 product with HCl, just instead of a hydrogen attached to carbon 1, it was another chlorine. So hopefully that makes sense. I'm gonna draw the rest of the products without showing the mechanism because it's gonna take a lot of time. If you want to see it for, does it matter which alkene you use? I mean, I would say unless he explicitly says use one or the other, you should probably do both like I have been doing, because I'm assuming both of them will react roughly the same amount. It's possible the less substituted one would react a bit more, but I don't know if that would be significant. There's a double bond there. And you should remember that the stereochemistry of this reaction, like the two halogens get added trans to each other, it's anti-stereochemistry. So for these 1,2 products, they should show that stereochemistry, but when we do the resonance form like this, we're working with cations, which are sp2 hybridized. They're trigonal planar, so like basically the chlorine here can be a dash or a wedge, and then when the chlorine attacks the positive charge here, it can also attack from the top or bottom. So I would say there wouldn't be stereochemistry. You might not really have to worry about that much detail, but just if you do want to worry about it, that's what the stereochemistry would probably look like for 1,4. And then the 1,4 from the other direction looks exactly the same because we're adding 2 of the same thing. So these 2 are the same thing, so you wouldn't really have to draw both, but you could like show the mechanism and see that it leads to this, which is the same thing. So I guess I'll write that. Okay, so like I said, only gonna show the mechanism now if you want me to. because it's the same exact thing every time. So I'm going to draw these as if we're reacting with this double bond. This is the 1-2 product. And then this would be, that's not a very good looking B. Sorry. This would be the 1-4 product, because again, we're numbering from that double bonds that we're looking at reacting. So hydrogen attached here, and then the bromine either attached here if there was no resonance, or down here if there was resonance. And both of these are actually the same if he names them, and if we looked at the reaction of the other double bonds, he'd also have the same exact stuff. So I wouldn't draw those if I was given this question, unless he said to like draw every single thing, but he'd probably put something like a methyl group here to give some sort of distinguishing to like the different positions on the ring, but as it's given, it doesn't really matter. And the last one. This is a 1-2 product if we were reacting with the double bond on the left. Oh, double bond still there. And then this would be the 1-2 product if it was reacting with the double bond on the right. So these are the 1-2 products. And then both of these are going to have the double bond in the same position. This would be if it was reacting with the one on the double bond on the right. And then this one would be like this, and that would happen if it was reacting with the double bond on the left, because I'm just numbering them to help you follow. Like, remember, 1 is the beginning of the double bond we initially reacted with, and the double bond in the resonance form always ends up in the same spot, so like that's why the double bond's in the same place, but the chlorine's in a different spot, and it would be named differently. And if you're wondering how you could get that, you should probably look at the mechanism in the resonance form for this. And if you're struggling with that, again, I can show you, but I don't want to belabor it because I showed an example. Okay, this is a bit of old stuff and new stuff from today, I guess, combined. What do you think this will do? We're reacting excess ozone and then zinc and hydronium with 2 double bonds. So what's going to happen? Cleavage, yes. And what kind of products are we going to end up with? There's multiple ways to cleave, and yeah, okay. So cleaving with ozones, when you cleave an alkene, will give you aldehydes and ketones. That's correct. So we can kind of draw lines like this to show like we're breaking those bonds. What? Okay. And then, actually, yeah, I'll just do it like that. Where you cleave the bond, you put carbonyl groups. So this is basically the fragments on the left. This here, that's what we have here. And then the other fragments, those 2 carbons, the single bonds between the 2 double bonds, are also going to form something. This is one way of showing it. So we have aldehydes here. Do you remember how to form carboxylic acids when you do cleavage of double bonds? That's something we should know too. KMNO4 and what else? Yeah, so I'll just, this isn't part of the question, but as a bit of review, because it will be on your final. Well, I mean, I don't know if the exact reaction will show up, but you should know it in case it does. Wherever you would get an aldehyde when you cleaved with, it's a weird way of drawing it. When you cleaved with the ozone, you get a carboxylic acid instead because it oxidizes the carbons. So you get this, and then just, it looks weird, but those are both carboxylic acids instead of aldehydes. So I specified we were using one equivalent up here, and that's why we only reacted with one of the double bonds. Generally, if he doesn't explicitly say, like, give the 1,2 and 1,4 products, and or if he doesn't put one equivalent, that usually means you have excess, but I'm also assuming he's going to explicitly say you're using excess just to make sure it's clear what's going on. But usually if it's not written, you just assume it's excess and it will react with everything. Just in case he doesn't write it, you should keep that in mind. Okay, so what does OSO4 and NaHSO3 do to double bonds? One, two diol, yeah. And what kind of stereochemistry do they have? You forgot, okay. So there's multiple ways to make 1,2 diols. I don't want to go over all those right now unless I end up having time, but when you use OSO4, you get a cis 1,2 diol, so the two alcohols that you add are cis to each other. And we're using excess, so we're going to get cis diols on both. So this is one product they could form. And suppose we get the two from one double bond is wedges, but then the other double bond gets dashes. Now like the 1,2 diols on one double bond are trans to the 1,2 on the other. So these are the two products. And if you drew like everything is a wedge, or I mean everything is a dash, or then you made the top ones wedge, the top ones dashes and the bottom ones wedges, like you could just flip the molecule and it would be the same thing. So that would be a waste of time. These are the two products. So can you go up to the last two of number 2? Sure. These two. Right. Okay, you're welcome. So remember, OSO4 is this 1,2 diol. I might have spelled that incorrectly. But yeah, those are characteristics that we considered with those reactions. All right. I'm assuming he talked about temperature and how it controls the thermodynamics and kinetics of reactions in class today. So I guess I can write it up here. If a reaction is done under high temperature, what kind of control is it under? Thermodynamic or kinetic control? Thermo, yes. So what does that mean? One-four is more likely, yeah, because it, I don't want to go over the reaction coordinate diagram idea, but you can just remember that high temperature means thermodynamic control means 1,4 is probably going to be the major product. And then by default, low temperature is kinetic control. This means 1,2 is the major product. And like this has to do with a reaction coordinate diagram. I'm assuming he went over basically when there's low temperature, the system has less energy available to it. And it kind of needs energy to do those resonance forms that lead to the 1,4 product. So it's just going to form it's going to form the product that's easiest to form because it doesn't have much energy, which is the 1,2 product. But when the temperature is higher, it has more energy, so it can do the resonance form and get the 1,4 product. So you can remember all that, and that might be good for a conceptual question, or you can just remember like what I have written here. So for his first reaction, what control is it going to be under? Thermodynamic or kinetic control? The temperature is 40 degrees Celsius. Thermo, yes, because this is high temperature. For context, you probably are going to see 40 degrees or 0 degrees, and 40 is higher than 0. So what kind of product are we going to see? I mean, it's given kind of there, but I guess I'll just say we're going to have 1,4 as the major product. And again, unless he explicitly says like react with this alkene or that alkene, I'd assume you should show both products. I don't know for sure. I didn't take the class with him, but I would assume that's what he'd want. So the 1,4 product has the double bonds like in the position between carbons 2 and 3 because again we went for a resonance form. So these are the two products, and this would be the 1,4 product if we were reacting with the alkene on the left, and then this one would be the double bond, the product from the alkene on the right reacting because of the way it's numbered. So if you had to work backwards, maybe he could give a question like that, figure out which alkene reacted to form this 1,4 product, just like number the thing with the halogen as 4 and then go backwards. I'm completely guessing. I don't know if he's going to do that, but I thought of it, so maybe that's a potential question. Great, so 0 degrees Celsius, we already established that 40 is usually thermodynamic, so this is going to be under kinetic control, which means we're going to see the 1,2 product. So we're just going to see the product we're used to seeing when we react HCl or HBr with a double bond. I put this methyl group here, and after posting it, I feel like I shouldn't have done that because it probably makes it a bit confusing. But not just confusing, but kind of up to debate. But I would assume that if we reacted with the double bond on the top, you'd end up with this product. Because even though you don't deuteroresonance form, the allylic cation here should be a bit more stable than the tertiary one because it has a resonance form. It just doesn't deuteroresonance form due to the kinetic control. But like maybe if you want to ask the professor about this specific one just to see what his thoughts are, you can do that. But my take on it is the allylic cation would be the more stable one, so the hydrogen ended up attaching here, and then that cation formed, and we got this product. And then here, there's not really a contest, like the allylic one should be more stable than the non-allylic one, so that would be the products there. Oh, it was bromine, not chlorine. Doesn't really matter, but I'll fix that. Are there any questions about these? Hopefully it's not too bad. So again, just remember that high temperature means it has no Markov-Nikov because of the allylic position. Again, that is my judgment on it. I don't know if that's what your professor would agree with, but like remember when you were going over the SN1 reactivities, he went over a diagram where he basically said a primary allylic cation is as stable, like equally as stable as a secondary cation that's not allylic. So like a secondary allylic cation is equally as stable as tertiary, basically. But I would still assume that we get this product I drew. I don't think he'd give you a substrate like this because it's pretty confusing, but you can ask him to see what his thoughts are, just in case he does give you something like this. I'm guessing there aren't any other questions. So this last one, for this question at least, it's 40 degrees high temperature. So it's going to be under thermodynamic control, which means we're going to get the 1,4 products. In both cases, the double bond is going to be where the single bond basically leading to the conjugation was. I'm just drawing the skeletons. There's one, and there's the other. This product, again, you can start numbering from the halogen to see which double bond it came from. It came from the double bond on the left. And then this one on the bottom came from the double bond on the right. So, yeah. And I'm pretty sure they would be named the same because the chlorine is on carbon 2 and then a double bond on carbon 3 in both cases, but I still drew both just to show both. All right. So number 5, we're looking at Thiel's-Alder reactions. Sorry, I was trying to make that go away. I guess that's not going to. So when you're doing a Thiel's-Alder reaction, you want to have a diene, a conjugated diene, which is what we've been looking at today. And then you usually want to have a, I don't know if you went over the terminology, but like this thing on the right is a dienophile. I might be spelling it wrong, but that's the term for it. It wants to react with a diene, just like an electrophile wants electrons. And you usually, I guess I'll go over to the side. I don't know how much of this you need to know because I don't know what he covered in class, but You usually want to have an EWG right next to the double bond, and this is an electron withdrawing group. If you didn't go over this in class, don't worry about it, but I don't know what he went over, so I'm covering it just in case. So something that withdraws electrons is something that's electronegative, like oxygen or chlorine or nitrogen, because of the dipoles they have and their polarity. They pull electrons away. And that makes the diene, like the double bonds here, more reactive with the conjugated diene over here. So that's a bunch of context for these reactions. In terms of drawing the product, what I was taught is like, that didn't look very good. I'm gonna redo it. The Diels-Alder reaction forms a sort of cyclic structure at the end. So you can do dashed lines like this to show like where the bonds are going to be forming. In the mechanism, it all happens in one step. It's basically like this. The electrons kind of go in a circle. I'm drawing the electrons going towards that bond that's forming to form the cycle. And then they're just going counterclockwise, basically. Everything is happening at the same time. So we get a double bond here now, which has changed position. And what? Okay, that was weird. It's not a perfect drawing, but something like this that should probably look better. I'll redo that bottom part. So we're basically just attaching the two rings to each other for the reaction. And I'm not sure you really have to worry about the electron withdrawing group factor, but just like in case he asks why it's there, it's just, it helps the reaction go. Oh, I should have given more space here. Okay, I'm gonna draw this a bit to the side. It just rotated the diene here because it's easier to see how the mechanism works when you draw it with the two double bonds kind of facing towards the right instead of towards the left like they were with how it was given. Was a bit of streaking. Okay, so it's gonna be the exact same mechanism, it's just different substrates now. Okay. Drew that towards the wrong bond. So again, just the electrons going kind of counterclockwise like this. And then the rings basically fuse. Okay, did not want to do that. Okay, so one other thing that I'm guessing he covered is the reaction is stereospecific. So like the double bonds we reacted with here, it says E double bond because like the hydrogens are pointing in the same direction and the other stuff is pointing in the same direction from that double bond. So it was cis at the beginning and it stays cis. So here where those two hydrogens are, or where they were, they still are, and they're still cis to each other. So you could either do them both as dashes or both as wedges, but they should be cis. Okay. So beyond just being able to show the product of these reactions and understanding the stereochemistry, I don't think you have to know too much, because I didn't, and is just learns this. I don't know how much you covered, but I'm assuming not much. If there are any questions about that, I can try to answer them, but I basically know as much as you guys learned today about this reaction. To be honest, it's not covered much in this class. It's looking like there aren't any questions about that. Okay. And the toluene and heat is just the conditions for that reaction, if anybody was wondering. So the last question is just another synthesis problem, because I'm sure there's going to be at least one on your exam, so it's good to practice. Does anybody have an idea of how to do this? Work backwards, so cleavage, yeah, we're doing cleavage. And what conditions are we using for it? O-free, yeah, because we have an aldehyde. There's a hydrogen here. I didn't draw in, but that's an aldehyde, so because of that, we don't want to use CamO-free. Just like before, this is a two-step thing. The first step is the ozone, and the second step is zinc and hydronium. Both of those are important. And we're reacting with some double bond. I guess we'll just put it here. And how can we get from this to that? I'll just show that that's how we cleaved it. So that reaction is used to add an alcohol to an alkene. We're working forwards. Yeah, so we want to go, that works. Acid would do, I mean, it would make the alcohol leave, but you don't know any reactions that would utilize that in this scenario for going to a double bond, as far as I know. But KOH is a reagent we can use, and the solvent is, did I draw an extra carbon on the product? Let's see. I have 1, 2, 3, 4, 5, 6, 7. That's a no. I did not. So remember, always count your carbons, and if you counted the carbons in the reactant and the product, you'd see that we didn't add any carbons, so we just did a cleavage reaction. All we had to do was get the alcohol to be a double bond and then cleave it. But the solvent for this reaction forming the double bond is important. Does anybody remember what it is? Well, not what exactly it is, but what type of solvent it is important. I know we already have, actually, we usually don't use KOH for this. Oh, now that I remember, there's a different solvent we usually use to form double bonds from alcohols. I'm guessing we don't remember though. Oh, yeah, okay, so an acid is correct. That's my bad. It's usually H2SO4, but H3O plus would probably work too. As far as I know, this is just what's commonly used. We usually heat it too. I think that's written as conditions to form a double bond from an alcohol, and this would do an SN1 or an E1 mechanism. Okay, so this synthesis wasn't too difficult, I think. Just the hardest thing is figuring out how did we get from a cyclic structure to that. We cleave the double bonds to open the ring. So if you ever start with a cycle and end with a linear thing, you should consider cleavage as a step in your synthesis. Don't have any other questions here, so that's everything I had planned for today. Honestly, went over that much. It is, yeah. I would just do a few practice problems. Like I said, he can't ask a whole lot because it doesn't get covered much. You really just, if you can understand the mechanism here, just like draw the dashed lines and then do the sort of cyclic electron flow that'll lead to the bonds that you see in the products. That's the extent you need to understand it too, besides the stereochemistry. There are practice problems in the book, I think, and I can probably put more of these. How come the first one isn't melded like the second one? Just because it would be hard to draw like that. It's easier to meld two cyclohexanes together. I mean, they're both melded, like they're both forming cyclic structures. Just, I don't know how I would draw something that looks like the one on the second one with this first one. It just, if you want to draw it like that, you can, but I personally don't see how I could make it look good. Actually, maybe I just drew that incorrectly. Now that I think about it, I might be wrong. Because I mean, I swear I remember seeing this in the book, but that might be incorrect. I don't really have time to check right now, but you might want to send this to your professor to see if it's correct or not, because like I said, I didn't cover this much in the class myself, so I have to be honest, like I don't have a lot of knowledge of this topic besides what you learned today. So it's possible that the product here looks more like this, but I mean, maybe it would be safer to draw it like this. It just looks weird. Because those aren't exactly the same. Yeah, maybe this would be better. Honestly, I'm sorry, just I don't like this topic because it was brushed over in my class just like it was brushed over with you, I'm sure. And you're going to be tested on it. At most, it'll probably be one question because he has to be aware that you barely learned anything about it, but just do a bit of practice so you have an idea of how to approach these. And I'll try to put a question on Tuesday's worksheet. Looks like people started leaving when I said I was basically done, but I wanted to ask if you guys had any topics you wanted me to cover on Tuesday, because I'm not planning on doing what I did like over spring break with a like dedicated review session going over just topics. I'd rather just make a worksheet and go over it like a regular session. But if I know what you guys are struggling with, I can know what to put on that worksheet because I'm going to try to cover as much as possible. Do you guys not know what you're struggling with? Or alkyne cleavage? Okay, I can go over that. I mean, I could go over a problem right now if you want to, but if you'd rather leave early, that works. Just, I can come up with a problem for that on the spot. Okay, I guess I'll go over that now. Because I still have like 20 minutes. If nobody else is interested in alkyne cleavage, you don't have to stay. But if you also have something you want to ask me, I can go over it because I have time and we're done with the worksheet. So I'm just gonna